Right, we'll continue with example 9 on page 12 here. Let's recap what we have learned so far in this chapter. Example 9 here will involve length of projection, so we'll also recap on how to find the length of projection. Right, so the main thing that we have covered yesterday is that for a three-dimensional line, we learned the vector equation, and it's written as r equals a vector plus lambda times another vector, where lambda is allowed to take all real values. The vector that is multiplied by lambda is known as the direction vector. And direction vector can be any vector that is parallel to the line. And this first vector here that is not multiplied by lambda is the position vector of a fixed point on the line. And so I just label it as A here. And this is what we call a fixed point on the line. Okay. Right, then we have also learned how to convert vector equation to Cartesian equation, and also the other way around. To convert vector equation to Cartesian equation, what we need is just to replace the r on the left hand side in the vector equation as a vector x, y, z. Let's say this is 1, 2, 3 plus lambda 7, 8, 9. Then the way to convert it to Cartesian, and recall the shortcut, you have minus and then the whole thing divided by the number in the direction vector. So you have x minus 1 over 7, y minus 2 over 8, z minus 3 over 9, then connect everything by an equal sign. Okay, we have also encountered some special situations where the direction vector has some zero component. In such a case, then when you write down the Cartesian equation, you will have to state that component separately, and that one we have covered it in example number 5 here. Example number 5 here, the y component of the direction vector is 0. So when we state the Cartesian equation, the y coordinate is stated separately. Because we cannot divide by 0. And so the y coordinate of the Cartesian equation, in the Cartesian equation, the y coordinate needs to be stated separately. It can no longer be written in a fraction form. Right, then when we need to convert Cartesian to vector, we need to first rearrange the fractions such that it becomes what I call a readable form. Then before you read the direction vector and also the fixed point on the line. Okay. And a bit in front here, in example 3, we have gone through the procedure on how to check whether a point lies on the line or not. The procedure is to substitute the position vector of the given point into the vector equation of the line. Then you try to solve for lambda. We have to solve for lambda 3 times because there are 3 equations that we can form. And then if the value of lambda we get, all 3 of them are the same, then we conclude the point lies on the line. If not all 3 answers for lambda are the same, then the point is not on the line. Right. We are going to use this technique a few more times later in this chapter. So you should remember the procedure of how to check whether a point lies on the line or not. You just sub the point into the line equation, solve for lambda, and see whether value of lambda is consistent or not. Okay. Right, then recall this part on projection. Right, now that we have already learned the vector equation of a line, then we can now understand projection better. Okay. Right, projection, the intuitive idea is a shadow, right? So if you're given a line L, which I draw using dotted line, if you're given a line L with direction vector B, this can be the direction vector of line L, and you have a vector A that may or may not be on line L, it doesn't matter. Let's say A is not on line L. Let's say vector A is not on line L, and you want to find the shadow of vector A on line L. Okay, and in the exam questions, we are usually only interested in getting the length of projection. We are not so interested in getting the direction. We are not so interested in getting the projection vector itself. We are usually only interested in knowing the length, right? So if the projection of vector A on line L, we are interested to know the length. You can always move this vector. You can always move it such that the starting point of vector A is now on L. If vectors are free, it can be moved around as long as length and direction remains the same. Right? So it's always fine to move a vector around. Okay, so you would move the vector A such that the starting point of vector A is on line L. Okay, then let's call this point as A, let's call this point as P. Okay. This green colored length will be the length of projection of vector A onto L. Okay. We can also say this is the length of projection of A onto the vector B. It means the same thing. Okay. Right, the formula for length of projection will be A dot B over B. Length of projection A dot B over B with modulus to everything. Okay, the modulus at the bottom means length, the modulus at the top is a usual modulus that converts a negative number to become positive. Okay. So always remember in the formula for length of projection, the vector B will be a vector that is parallel to the line that you want the shadow to be on. Okay, while the vector A is the slanted vector whose length of projection you are interested in. Okay. Right. Okay, let's continue with example 9 here. Okay, before that, we have also gone through the foot of perpendicular yesterday. So make sure you can still remember the procedure, and we will implement this procedure, these 4 steps under method 1 in example 9. Okay. Okay. The line L1 passes through points A and B with these 2 coordinates. L2 has this vector equation. Okay. Right. So part 1 says find the length of projection of AB onto L2. Okay. So when you are given these 2 information about the 2 lines, we are not sure whether the lines will intersect or not. Okay, we are not sure whether these 2 lines will intersect or not. Later in this chapter, in the next few pages, we will learn that it's possible for 2 lines to not intersect at all. Right? Well, in this question, we don't really need to know whether the line L1 and L2 will intersect or not. We don't really need to know. Okay. It is the vector AB that you want to project onto L2. So let's find the vector AB first. And then whether or not the vector AB starts from the line L2 is not important, because even if AB is somewhere outside the line L2, you can always move the vector. you can always move the vector such that the starting point lies on L2. Right, so yeah, we don't really have to know whether L1 and L2 intersect or not. Okay, so let's find vector AB. This is OB minus OA. We just sub in the coordinate. For the line equation of vector, for the vector equation of line L2, let's convert it to a more familiar form. The parameter is t, so this pink colored part will be the fixed point on the line L2, 550. T is a parameter, 2 minus 1, 0, and t is in R. Okay. Now, let's visualize a simple diagram. No marks are given for the diagram, but it's usually helpful to visualize. So I just simply draw a line L2. This is where I want to project my vector AB on. Right, so I have a vector that is parallel to L2. That will be the direction vector 2 minus 1, 0. Okay. Now, in my vector AB could be somewhere outside the line, or it can be on the line L2. I'm not sure. Okay, but anyway, let's just move it such that now the vector AB, has a starting point at L2. Okay. So what is this red color vector? It is minus 5, 4, 1. Okay. To find the length of projection, it will be this blue color line here. Okay. Now, according to the formula for length of projection, and let's write first the words length of projection of vector AB onto L2. Okay, the formula says is A dot B over B. What are the A and B in the formula? The A is the slanted vector whose shadow we want to find. So in this question, the vector AB, the red color vector, is the vector whose shadow we want to find. And so that would be AB dot with the direction vector of L2, 2 minus 1, 0. Then take the modulus. Right, and next, you divide by the 2 minus 1, 0. Okay, so here we are implementing the formula of A dot B over B. We're implementing the formula of A dot B over B where A, or the first vector that we use here, is the vector whose shadow we want to find. And the second vector we use is the direction that is parallel to the shadow. Yeah. You can always refer back to the diagram on page 4 of your notes and to see how we actually use the formula. Okay. Now let's type in the numerical values and do the computation. Okay, vector AB is minus 5, 4, 1 dot with 2 minus 1, 0. While at the bottom, you can implement the length formula. Now at the bottom, we have square root of 5. At the top, show your working in computing the dot product. At least write down that you are summing up three numbers, minus 10, minus 4, plus 0. Okay, you have minus 14 with a modulus above. That means it becomes positive 14 divided by Z5. And it's good enough to leave your answer this way. And since they didn't say that it's compulsory to rationalize a number, it's okay to leave it this way. Of course, there's nothing wrong if you want to convert it into 14 Z5 over 5. This should be the rationalized form of the number. Either way will do as a final answer. And that's it for part 1. Finding the line of projection, we are done. Okay, now I will carry on with part 2. To those who have just joined this meeting, if you came in late, please remember to watch the recording and for the early parts that you missed today. Okay. Now for part 2, we are finding the foot of perpendicular this time. In this question, again, the whether or not L1 or L2 intersect is not important for us to know. Okay. For part 2, what's important is just the point B and the line L2. You don't really have to care about the line L1. So if you want to visualize, what you need is only the line L2, which we know the direction vector, is 2, -1, 0. You have an external point of B. Although they didn't say very clearly that B is actually an external point that doesn't lie on L2, but from the way they ask the question, if they ask you to find foot of perpendicular from B to L2, then B of course must be an external point. Because if B lies on L2, then there's no foot of perpendicular to find anymore, right? So B is guaranteed to be an external point because they ask for a foot of perpendicular. So you need the external point B then, which is having coordinate -3, 5, 6. Draw a foot of perpendicular which I label as F, and let's introduce what is F. Okay, so we have to tell the reader what we mean by the point F here. Okay. Because F is not a standard symbol. You can name your foot of perpendicular to be N or whatever other symbols you like, right? So let's introduce point F. Let F be the foot of perpendicular from B to L2. Okay. According to the procedure on page 10, according to the 4-step procedure on page 10, okay, to find the foot of a perpendicular, first thing is to notice that F lies on the line L2. F must be a point on line L2. So let's say here, F lies on line L2. Okay, so if F lies on line L2, the vector OF must satisfy the vector equation of L2 for a particular value of lambda. Okay, so we can say, so OF is equals to, okay, so here we are using, we are substituting vector OF as the vector R in the vector equation of line L2. Okay, we are using OF to replace R. Okay, and we are sure that this equation will hold for a particular value of the parameter, in this case is t. Okay, so OF is equal to 5 plus 2t, 5 minus c, and 0 for some t in R. Okay, so by writing for some t in R, what we really mean is this equality would hold for a specific value of t. If you're wondering where this 5 plus 2t, 5 minus t are coming from, it's actually coming from here, in the vector equation of line L2. Okay, then we have to make use of the 90 degrees. Okay. For 90 degrees, we know that the dot product of two perpendicular vectors are 0. So before that, of course, you need a pair of perpendicular vectors. Okay. So obviously, the red color direction, either FB or BF, will be perpendicular to the direction vector of L2. So let's find the vector either BF or FB. Either one will work. Okay, so I'll just find BF here. BF is OF minus OB. OF, we already have the expression in terms of t, so let's just use it. OB is minus 3, 5, and 6. And then just simplify the numbers. Okay. Now, next thing is we want to use the 90 degrees. And so we notice that the vector BF is perpendicular to the line L2. That means uh, the vector BF dot with the direction vector 2 minus 1, 0 will be equal to 0. BF dot with the direction vector of line L2 will be equal to 0. Okay. So notice that when we use the dot product, the two terms, the two objects that you dot them together must be vectors. It is wrong to say BF dot L2 equals 0. This thing doesn't make sense because you cannot take the dot product of a vector and a line. L2 is a line, not a vector. Dot product can only operate on two vectors. And so make sure when you use dot product, you are dotting two vectors together. And when you say perpendicular, it's fine to use L2. Okay. What is BF? Let's type it in. There's 8 plus 2t minus t and minus 6 dot with 2 minus 1, 0 is equal to 0. Let's compute the dot product, expand it, you get 8 plus 2t times 2 plus t plus 0 equals 0. And then you get 5t equals negative 16. T is negative 16 over 5. Okay, just continue over here. Right, now that we have already found the value of t, earlier at the beginning we say OF is equal to 5 plus 2t and so on for a particular value of t. Now we have found that particular numerical value of t. So let's sub it back into the expression for OF. Right. So we say sub t equals to minus 16 over 5 into the expression for OF. Okay. So I'm substituting into the pink color expression that I circled above. So now we have OF equals to 5 plus 2 minus 16 over 5, 5 minus 16 over 5, and 0. Okay, so after doing the computation, you should get minus 7/5, 41 over 5, and 0. Okay. The question is not asking for the position vector of f, it's asking for f itself. And so your answer should be given in coordinate form. And they ask for the foot of perpendicular, so they expect the answer given in coordinate form. Okay, because it's not asking for position vector. Okay. So at the end, you just need to convert the answer into coordinate form. Foot of perpendicular from B to L2 as coordinates minus 7/5, 41 over 5, 0. And convert your answer to coordinate form. Right. Jindra asked a question in chat. I saw that. Yeah, I'll respond to that in a few seconds. Okay, I leave this screen on for a while first, and for everyone to jot things down. Okay, so this is the procedure of finding foot of perpendicular. In this chapter, we are going to implement this procedure again and again, and many times. There will be many questions that involve finding the foot of perpendicular. Okay, so it's always these few steps. First is to introduce the point f. Then notice that f lies on L2, so it would satisfy the equation of line L2. Then you would get OF in terms of the parameter. Next step, get a vector in terms of t, where the vector is perpendicular to the direction of L2. Okay. So you either get BF or FB, vector BF or vector FB in terms of t. Then take the dot product of the pair of perpendicular vectors, set it to 0 due to the 90 degrees. Then solve for that specific value of t. After you get the t, at the end you sub it back into the expression for OF, then that will give you the coordinates of f. Okay, depending on whether the question is asking for position vector or coordinate, you would then write your final answer in the correct form. Okay, if they want a position vector, then you can just leave it in vector form. Okay. Right. So regarding why we can sub OF into R in the vector equation of L2, let's recall from an earlier page. That will be page 5. Page 5, the middle of the page, point number 3. Okay, it says if a point lies on line L, then, okay, so here the line equation is given as R equals A plus lambda B. Here says if you know that a point P lies on L, then you can replace R by OP. You can replace R by OP because let's recall the idea of vector equation of a line. Okay. Now, okay, let me name this direction as B and let me call this point as A. Okay, so vector equation of a line can be written as R equals OA plus lambda times vector B. where lambda is in R. Now, if I tell you, let's call it F here, if you are given that F lies on line L, then we can say OF can be written as OA plus lambda B for a particular value of lambda. Okay. So let's imagine this. You have O somewhere far away. I'm not sure where O is. Okay. So if I want to get from O to F, okay, let's focus on this green box here. If I want to get from O to F, I can travel from O to A first. I can travel from O to A first, which is what I have here as a first term. Okay. Then followed by a scalar multiple of B. Right? Yeah, this very thick black color vector is just a lengthened version of B. In other words, a scalar multiple of B. Or in other words, lambda B for a specific lambda. Yeah, that's why this thing makes sense. You can get from O to F by taking the path O to A followed by a lengthened version of B. Yeah. So if F happened to lie on the other side, right, then it's also a scalar multiple of B, although this time the lambda will be a negative number. Yeah. And so it will still work. And so just remember that whenever you are given a point on the line, you can use the position vector of that point to replace R in the vector equation of the line. And we are going to use this technique again and again in the later parts of the chapter. And so you should be familiar with this. Okay, now let's move to example 10. On page 13. Okay, relative to origin O position vectors of A and B are these two. So you're given this is vector OA, this is vector OB. The line L passes through point B parallel to this vector. So by saying that the line L is parallel to this vector, that means this vector can be taken as direction vector of L. Okay, write down vector equation of line L. This one is very easy. No computation needed because all the information are already available. Okay, if you visualize your point, your line L, it says line L passes through point B. In other words, point B lies on L. Okay, so B is a point on L. B has coordinate minus 7, 2, 3. And you also have direction vector of L, which is 2, minus 1, 0. Okay, so two complete information available already. So just write down the vector equation straight away. The vector equation of line L is R equals to uh, the fixed point plus lambda times the direction vector, lambda in R. 2 minus 1, 0. Fixed point is minus 7, 2, 3. Okay, done. Okay. It is a must to state this sentence, vector equation of line L. If you do not state this pink sentence, then at least you should write L colon. You should write L colon. If you already state vector equation of line L, then it's okay not to write L colon here. Yeah. If you want to write both, of course, there's no problem. If you still want to write L colon here, then of course no problem. As long as you make it clear that you are writing the equation of line L, because there could be many different lines involved in this question. Okay. Part 2, find position vector. At this time, they want your answer in vector form. Find position vector of the foot of perpendicular from A to L. Okay. You have the coordinates of A because the vector OA is given. A must of course be an external point, and no doubt about that because they are asking for a foot of perpendicular. A must be an external point. Okay. So you can use back the same diagram in your visualization here. Let's just draw a point A, that is somewhere outside the line, and try to avoid drawing A at a position that is perpendicular to L at point B because the question doesn't say that. The question doesn't say that the foot of perpendicular of A is point B, so you can't simply assume, right? Right, so it's better to position your A somewhere away from B, so that the foot of perpendicular doesn't overlap with point B. And we can't simply assume that F and B overlap because question doesn't say that. Anything that the question doesn't say, we can't simply assume. Okay. So let's call this F. Okay. So let F be the foot of perpendicular from A to line L, from A to L. Okay. Then follow the usual procedure again. The 4 steps. F lies on L. Okay. So OF can be used to replace R. OF can be used to replace R in the vector equation of line L, and this will hold for a specific value of lambda. Okay. OF is equal to minus 723 plus 2 lambda minus lambda, then 0 lambda is okay not to write, for some lambda in R. Okay, next step, get a vector that is perpendicular to the line L, which is vector AF or FA, whichever you prefer. AF is equal to OF minus OA, then just compute. Wait, I have to minus by OA. Minus by OA. A, we have the coordinates given as minus 6 minus 1, 5. Minus 6 minus 1, 5. Okay, yeah. So just be extra careful when you do your computations because it's easy to make careless mistakes. Although the computations are rather easy, it's just simple plus or minus. Just be extra careful. Okay. Then next we make use of the 90 degrees, noting that AF is perpendicular to line L, which means your AF dot with the direction vector, you can already sub in your AF actually. Minus 1 plus 2 lambda, 3 minus lambda and minus 2, dot with the direction of L is equal to 0. Okay, let's compute this dot product. Minus 3 plus lambda and plus 0 equals 0. And then solve for lambda. 5 lambda minus 5 equals 0. That gives you lambda is a nice number of 1. Okay, I don't want to scroll too far down. Let me just continue on the right here. I will now sub lambda equals to 1 into the expression for OF. The expression for OF is the pink color that I circled up there. And OF will be minus 7 plus 2 times 1, 2 minus 1 and 3. Okay, and done. And they are asking for position vector. They're asking for position vector, so our answer can be left in vector form. And we have already introduced f as the foot of perpendicular. So OF will be understood as the position vector of the foot of perpendicular. Okay, now I will move to part 3. Okay, A prime is the reflection of A about the line L. Okay, now we want to reflect a point about the line. Find the position vector of A prime. So you can refer back to your same diagram. It's the same point A that you want to reflect, and it's good that the F has already been found. The F has been found, so what we need is just to extend this dotted line to the other side to get A prime, where F is the midpoint of A and A prime. But since F has been found, it's very easy to do part 3. I just paste this diagram down there. Okay. Point F has been found to be, we can read from the vector OF, that's minus 5, 1, 3. And then make use of the midpoint formula. Okay. Since they have already introduced the meaning of the point A prime, there's no need for us to introduce A prime inwards. And so we can straight away start with the computation by noticing that F is the midpoint of A and A prime. So OF is equal to half times OA plus OA prime. Rearranging the formula, 2OF is OA plus OA prime. OA prime is equal to 2OF minus OA. Okay, then now we can do the computation. And that's it. And this is a position vector of A prime. The answer can be left in vector form because they're asking for a position vector. And if you want to make your answer more complete, of course, at the end you can say position vector of A prime is this minus 4, 3, 1. But this is optional to write. Okay. Right, we're about to start a new section on interaction between two lines that's on page 14. Okay, maybe before that, it's good to take a break. Uh, we'll now take a break. When we come back from the break, we'll start page 14 on the interaction between two lines. During the break, you can read through page 14 first. Later, I will explain. Yeah, I start the timer now. Right, hi everyone and welcome back. We'll continue with page 40. Okay, so we'll now study the relationship between two lines. So earlier we have covered the interaction between an external point and a line. Now we cover two lines. Okay. Um, there are four possible relationships between two lines in a 3D space. Okay. So this is more complicated than 2D because in 2D there are not so many possibilities. Maybe I should show you for two dimensions first. Okay, for two-dimensional lines, when you have two lines, right? Um, okay, for 2D lines, uh, let us say I have a usual XY plane here. Um, if this is L1, this is L2, here's the first possibility where they are intersecting lines. Okay, intersecting. Okay, second possibility, this is parallel, uh, but not coincident. And we also have the third possibility, where L1 and L2 exactly overlaps. Okay, so this one we call them coincident lines. Okay. So for 2D lines, there are three possibilities. They can be intersecting at one point, parallel, or coincident. Coincident means overlapping. Okay. Now for 3D lines, not only we still have these three possibilities, but there is a fourth possibility, which is skew lines. Okay. So you can imagine in a three-dimensional space, it is possible for two lines to never intersect, even though they are not parallel. Okay, in 2D, whenever two lines are not parallel, they are guaranteed to intersect as long as you extend them long enough. Okay, in 2D, if you have a line like this is L1 and this is L2, L1 and L2 are not parallel, then once you extend the lines long enough, they are guaranteed to intersect. That's for 2D. That's for 2D. Okay, but for 3D, it's possible for two non-parallel lines to never intersect no matter how long you extend them. And so yeah, you can just imagine in the usual 3D space, uh, and you have a straight stick and another straight stick which are held at two different slanted angles, two different angles. But then it's possible to hold the two sticks in a way that they don't touch each other in the 3D space. Right. So in 3D it's a bit hard to visualize. For 3D, there is a fourth possibility of being skewed. So let's say my L1 is here. Then my L2 could be somewhere below here. Yeah, your L2 could be somewhere below here at a different height. So in 3D, it's possible for two lines to be not parallel and don't intersect. And in such a case, we call them skew lines. Okay. Okay, the other three possibilities are still there for three-dimensional lines, and it's also possible for 3D lines to intersect at a point. It's also possible for 3D lines to be parallel and not coincident. And it's also possible for the two lines to be the same line, or in other words, coincident line. Okay. So there are four possible relationships for 3D lines. Okay, the new fourth possibility is skew lines. Skew lines means they are not parallel and they don't intersect. Okay, so let's go back to the notes and see. I think I've already um, explain the meaning of the word intersect. Intersect means they have one point in common. Uh, so when we use the phrase intersecting lines, we mean they have one point in common. When we use the word parallel lines, then it means they have the same direction but no point in common. In other words, never intersect. So parallel lines never intersect no matter how long you extend them. Coincident lines means they are essentially the same line. So, or in other words, they have the same direction and they have infinitely many points in common. Because they completely overlap. They completely overlap. So there are infinitely many points in common. Okay. Point number 4 says lines that are not parallel, don't intersect, and are not coincident are called skew lines. Okay. Okay, so let's drill further into intersecting lines. Okay. Okay. So first thing that you need to know is two non-parallel lines may intersect at a point. Here I use the word may. I'm not using the word must. I'm not using the word must. So it's possible for non-parallel lines to not intersect for 3 dimensions. So yeah, two non-parallel lines may intersect at a point. Okay. So we need a procedure to check whether two non-parallel lines may intersect or not, because it's not a guarantee that they must intersect. Okay, so you need to be familiar with this procedure of checking whether two lines intersect or not. You need to be familiar because it will be asked in the exam. There are many exam questions that ask you to show that two lines do not intersect. Or sometimes they ask you to show that the two lines intersect at a point. So you need to be familiar with this checking procedure. Okay. The steps to check whether two lines are intersecting, the first thing is you would equate the two vector equations, just like normally how you equate two linear equations to find the intersection. Here is the same idea. It will equate the two vector equations, which means uh, you will equate this with this. The two yellow color parts, you will equate them since they have the same left hand side. Okay. Then next is you would solve two of the three equations formed simultaneously to find the values of lambda and mu. Okay, so um, okay, L1 R is equal to something plus lambda something. And for L2, you have R equals to something plus mu something. Okay, when you equate this and this, you are going to have a vector in terms of lambda equals to another vector in terms of mu. Okay. Then you are going to get three equations by equating component by component. You're going to get three equations in terms of lambda and mu. Okay. Then the procedure is you should solve two out of the three equations. You should pick two. So you have equations 1, 2, and 3. An equation called equation 1, equation 2, and equation 3. You will pick two equations. Pick two equations out of the three to solve for lambda and mu. Okay. Now, one very important thing is once you pick the two equations, let's say I pick 1 and 2, then in my process of solving for lambda and mu, I should never touch equation 3. I repeat, once you pick your two equations, you never touch the third equation. Once you touch the third equation, everything will be wrong. The whole procedure will go wrong. Right? So make sure to leave the third equation alone. Don't touch equation 3. Of course, it's not a must to select 1 and 2. Let's say if I select 1 and 3, if I select equations 1 and 3, then I should never touch equation 2 when I solve for lambda and mu. Okay. Because the equation that you don't touch is reserved for checking purpose. Let's read point number 3 up there. Okay, so after you solve 2 of the 3 equations, you will get a value for lambda and mu. You will get lambda equals to a number, mu equals to another number. Then you would sub the number of the values of lambda and mu that you got into the third equation to check whether the left hand side is equal to the right hand side for the third equation. Okay, if the two sides are equal for the third equation, you can conclude that the two lines are intersecting. If the two sides are not equal, then the two lines are not intersecting. Okay. For the case when the two lines are intersecting, you can then use the value of lambda and mu to sub back into either of the two equations of L1 or L2. You can sub those values of lambda and mu that you found into either of these two equations to find the intersection point. Okay, so this is the procedure, and later we'll do some questions on this. Okay. Now let's carry on. This page is to introduce to you the concepts first, and we'll do example questions in the later pages. Okay, so we have covered about intersecting lines. The important thing to learn about intersecting lines is how to check whether two lines are intersecting or not. Okay. Then next is parallel and coincident line. Okay. So if the direction vector of two lines are parallel, so first of all, when I say direction vectors are parallel, it's not a must for the direction vectors to be exactly the same. Okay, so let's say this direction vector is given as 1, 2, 3. If this is given as 2, 4, 6, then these two direction vectors are parallel. Because they are scalar multiples of one another. They are scalar multiples of one another, so they are parallel. So it's not a must for direction vectors to be the same. We only need the two direction vectors to be parallel so that we can say that the lines are parallel. However, this sentence tells us if the direction vectors are parallel, then the two lines are either parallel or coincident. There are two possibilities. Because for two parallel lines, okay, when we use the phrase parallel lines, it's understood to be separate parallel lines. Okay, so there is this possibility that they can be separate parallel lines. Okay, however, there is also a second possibility where the two lines are actually the same line. Okay, so if the two lines are the same line, then their direction vectors are of course also parallel. And so you can have a B1 this way, B2 this way. Okay. So you can have this second possibility of two lines being coincident. So that means that if you are able to show that the direction vectors are parallel, that's not good enough for you to conclude that the two lines are separate parallel lines, because there is a possibility of them being coincident. Coincident lines can have the same direction vector. They can also have different direction vectors which are parallel. The idea is direction vectors are parallel, not necessarily the same. We only need parallel. So you can have like 1, 2, 3, and 2, 4, 6. Because even if it's the same line, a same line can have different direction vectors as well. Direction vectors are always replaceable by any other vectors parallel to it. Okay, so yeah, so conversely, here we say if two lines are either parallel or coincident, then we can deduce that their direction vectors must be parallel. Okay. So the logic is this: if direction vectors b1 and b2 are parallel, then we can deduce that the lines L1 and L2 are either parallel or coincident. And same goes the other way. And so if you are told that L1 and L2 are parallel, then you can say direction vectors B1 and B2 are parallel. If you are told that L1 and L2 are coincident, you can also say that direction vector B1 and B2 are parallel. Okay. So the logic goes both ways. Okay. Then okay, the direction vectors of the two lines are parallel as shown in the diagram here. This means that B1 is a scalar multiple of B2 for some scalar k, which means their direction vectors are scalar multiples of each other. Okay. Okay, later on page 15, we will learn how to show that two lines are distinct parallel lines. A distinct means different. And so in example 11, we'll show that the two lines are actually separate parallel lines. Okay. Uh, Now let's go to the last part of page 14. Okay, to show that two lines are skew, there are two things that you need to establish. Okay. This is also very important because in the exam, there are many past year questions that ask you to show that two lines are skew. And so to show that two lines are skew, there are two things that you need to establish. To show that two lines are skew, we need to show that first thing, they are not parallel. L1, L2 not parallel. And the second thing, L1, L2 don't intersect. Two conditions to show. You have to establish these two conditions. It's an AND connector here, so you have to establish both. Then only you can conclude that two lines are skewed. And so skew lines must be not parallel and don't intersect. You need both conditions to hold. Okay. Move to example 11. Okay, in this question, the solution here is partially printed for you. But I will just do the whole thing from scratch. Because the way I want to present my answer will be a little bit different from the printed version, but it's actually the same idea. So I will just do the whole question from scratch. Now, before I start doing this, let me tell you the idea first. They want us to show that L1 and L2 are distinct parallel lines. Okay, so here the question particularly mentioned the word distinct, which means they want you to show that not only the direction vectors are parallel, you have to also show that they are not coincident. You have to rule out the possibility of them being coincident. Okay. So the whole idea is this. First thing is to compare their direction vectors. Compare their direction vectors and notice that these two are actually parallel. And by noticing that one is a scalar multiple of the other. Okay. So that's the first thing to do. Okay, so after you show that direction vectors are parallel, there are two possibilities. You can have the two lines coincident, or you can have two distinct parallel lines. Because in both of these diagrams, I can have my B1 pointing this way, B2 pointing the other way. B1 this way, B2 the other way. So the next thing is we have to eliminate this possibility. We need to rule out this possibility. So that we can conclude that they are distinct parallel lines. Okay. Now, how to rule out the possibility of the two lines are coincident, and how to show that they're actually not coincident? Okay, so in the partially printed solution there, I said there are two methods. And whichever method you want to use is actually up to you. Okay, so uh, yeah, before I really show you the proper working, I tell you the idea first. Okay, so uh, let's assume that we have already shown that the direction vectors are parallel, and now we have these two possibilities to consider. Okay, if they are distinct parallel lines, okay, uh, there will be a point, let's call it point A1, a fixed point A1 on the line L1, and a fixed point A2 on the line L2. There will be a fixed point that you can read from the vector equation. This will be the point A1, this will be the point A2. So um, if there are distinct parallel lines, then the vector connecting A1 to A2, no matter where you place your A1 and A2, the vector connecting A1 and A2, it is guaranteed to be not parallel. This one is not parallel to B1. It's guaranteed to be not parallel to B1. And because B1 and B2 are parallel, then it's of course also not parallel to B2. No matter where you place your A1 and A2, as long as these two are separate parallel lines, then the orange vector that you get, whether it's pointing this way, this way, this way, or this way, yeah, it will never be parallel to B1 or B2. Okay. So that's the idea, right? So if you are able to show that the vector A1, A2 is not parallel to B1, then it's good enough to conclude. Because if it's not parallel to B1, then of course it's also not parallel to B2. Because B1 and B2 are parallel, right? Okay. Then that's the first method. Okay. Okay, the second method is okay. Wait, still on the first method. Why the first method works is because if you see, if the two lines are really coincident, referring to the diagram on the left, if you have your point A1 here and point A2 somewhere here, then the vector A1, A2, for the case when they are coincident, it will definitely be parallel to B1 and B2. Right, so if it's not parallel, if A1 and A, if the orange vector is not parallel to B1 and B2, then of course there are two separate parallel lines. Okay. Okay. Now, let's move on to method 2. Okay. Method 2, the idea is that you need to show that the point A1 doesn't lie on line L2. Okay, so you can imagine this. If they are separate parallel lines, then obviously A1 will not lie on L2. A1 is not on L2. If you can show A1 is not on L2, then of course there must be distinct parallel lines already. Because for the case when they are coincident, coincident means L1 and L2 exactly overlap. And so this same line is L1 and also L2. So A1 lies on L2. If they are coincident line, A1 must lie on L2. And so if you can show that A1 doesn't lie on L2, then they must be distinct parallel lines. Since now we only have two possibilities. So if it's not the first, it must be the second. Okay. Okay. Yeah. Okay. So after knowing the idea, now I will present my working. Okay, the way I present my working here will be slightly different from the printed version, although it's the same idea. Okay. But in the printed version, they are naming the points. They are naming the points. This point as A, this point as B. It's just for easier referencing. Okay. Um, okay. So the first task to do, okay, this time I decide not to name the points first, lah. Okay, I will only introduce the names when it is necessary to do so. Okay. So now I will just compare the direction vectors first. So the first task, okay, the first task, the green part you don't have to write. I'm just telling you what I'm doing. The first task is to show that direction vector of the first line. Okay, here's L1. They already named it L1 and L2. And so this is actually L1. This is L2. Okay. Show that direction vector of L1 is parallel to direction vector of L2. Okay. Now, so in our working, we can say, note that I'm going to compare these two direction vectors. But it's easier to factor out a -2 from the second one. 1 minus 2, 1. So the direction vector of L2. Okay, so we have shown that one vector is a scalar multiple of the other. That means these two vectors are parallel. So we say the direction vector of L2 is parallel to the direction vector of L1. Yeah, I'm using some short forms here. I'm using DIRVEC as direction vector. In the exam, you better write the full word. Okay. Okay. Hence, L1 and L2 are either distinct parallel lines or coincident lines. And now I state the two possibilities. Now move on to task 2. Task 2 is to rule out the possibility of L1, L2 being coincident. Okay, so here if you use method 1, method 1 is to construct a vector connecting one point on L1 to another point on L2. And noticing that this vector is not parallel to the direction of L1 and L2. Okay. Now I find it useful to name some point here. Yeah, the printed solution named the point as A and B. I prefer to name it as A1 and A2. Uh, So I will just let OA1 be equals to the fixed point of on L1, that's 0, 4, 1. OA2 be 1, 0, 2. Okay, then A1 lies on L1 and A2 lies on L2. Okay. Construct the vector A1, A2. That is OA2 minus OA1. Then we say, note that 1 minus 4, 1 is not a scalar multiple of we want to compare with either B1 or B2. We want to compare with vector either B1 or B2. Okay, let's compare with B1 here. It's 1 minus 2, 1. Okay. Now, if you need to show that two vectors are not parallel, what the syllabus expects you to write is only a sentence. The syllabus doesn't expect you to show computation for the case when two vectors are not parallel and they want to state that they are not parallel. They only require you to state it in a sentence form. There's no need to do any computation. It's based on our syllabus requirement. When you want to show that two vectors are parallel, like the case above here in blue color, to show that two vectors are parallel, you have to show that one vector can be written as a number times the other vector. But when you want to show that they are not parallel, no computation is needed. You just need to say that note that one vector is not a scalar multiple of the other. Then that's good enough. Okay. I think it should be very clear just by looking at the numbers. You know that this vector is not a scalar multiple of the other. One very obvious thing to see is that they have the same x component. They have the same x component. So if you really set 1, 4, 1 to be k times 1 minus 2, 1, for the first component to be equal, you are supposed to set k to be 1. But then if k is 1, minus 4 is not equal to 1 times minus 2. Yeah, so that means you can never find a consistent k. You can never find a consistent k that will make the equality hold. Right, so because it's so obvious that one vector is not a scalar multiple of the other, the syllabus doesn't require you to show any computation. You just need to state in a sentence form. Okay. So it's usually very easy to see when you have two components being equal. You have the same x component in the two vectors. I give you one more example. Let's say I give you 3, 4, 5. And I give you another vector. Let's say this is 5, but this is, let's say, 3, 2. This one is also obvious that these two are not scalar multiples. This and this are not scalar multiples of each other. Because if you really set them to be equal, and you put a k here, then because they have the same z component, k is supposed to take the value of 1. But then when k takes 1, 4 is not equal to 3. 3 is not equal to 2. So that means you can never find a consistent k. Yeah. So it's very easy. When you have one component being the same, then if they are indeed scalar multiples of each other, then the other two components must also be the same. Right? So in this case, since the z components are the same, but the xy components are different, then you can straight away say that they are not scalar multiples of each other. Okay, our syllabus doesn't require you to really solve for the k. Okay, they just require you to state it in sentence. Okay. Right, so yeah, you just need to state in sentence and note that 1 minus 4, 1 is not a scalar multiple of 1 minus 2, 1. Therefore, vector a1, a2 is not parallel to okay. So we have shown that vector a1, a2 is not parallel to the direction vector of L1. That means yeah, you have a diagram like this. This is L1, this is L2. Here's B1, and here's possibly B2. Okay, here's your A1 and A2. Okay, we have shown that this A1, A2 vector is not parallel to B1. That means the vector A1, A2 is not parallel to the lines L1 and L2. Okay, and therefore, they must be separate parallel lines. Okay, and we are done. This is under method 1. Okay, this is under method 1. Okay, before I move on to method 2, about this yellow colored sentence here, there are other ways of writing this sentence. There are other ways of writing this. Okay, alternative ways to write this sentence. Okay, so one alternative way to write this sentence is that you can also say 1 minus 4, 1, and the other vector are not scalar multiples of each other. Another way to write this is similar to the one printed for you. You can also say 1 minus 4, 1 is not the same as k times 1 minus 2, 1 for all real values of k. So if you want to use the uh, second alternative way to write the sentence, then you have to write for all real values of k, which means regardless of what value of k you choose, uh, the left hand side and the right hand side can never be equal. Okay. Okay, now I will move to method 2. Uh, Chandra asked, will there be questions where they would ask us to use specific method? For this kind of question, they won't force you to use a certain method. It's actually your choice. Okay. Okay, so let's move to method 2. Okay. So assume that task 1 has been done. Okay. Whether or not you use method 1 or method 2 for task 2, task 1 must still be done. Okay, so let's assume that task 1 is done. Then when we do task 2, we use method 2. Okay. Okay, task 1 must be done first. Okay. The method 1 and method 2 are for task number 2. Now, for method 2, some people may prefer this because it's kind of easier to understand. Um, for method number 2, we just need to show that the point A1 doesn't lie on L2. A1 not lie on L2. For all and for any means the same. To answer Shu's question, for all and for any, they are interchangeable. If you really think about it carefully, for all and for any means the same. Okay. So under method 2, we'll show that point A1 doesn't lie on L2. Of course, you can also show point A2 doesn't lie on L1. Okay. Now, so here we will also need to introduce the point A1. So I will let OA1 be 0, 4, 1. Then A1 lies on L1. Okay. Now, we want to check whether A1 lies on L2. Okay. So we would set R equals OA1 in the vector equation of L2. Okay, we have uh, 0, 4, 1 equals to 1 minus 2 mu, 4 mu, and 2 minus 2 mu. Solving for mu, 0 equals 1 minus 2 mu, which means 2 mu equals 1, which means mu equals a half. 4 equals 4 mu, which means mu equals 1. 1 equals 2 minus 2 mu. This is minus 1 equals to minus 2 mu, which means mu equals a half. look at these three values. They are not all the same. So we say, uh, since the value of mu is not consistent, we deduce that A1, point A1, or simply just A1, it does not lie on L2. Therefore, L1 and L2 must be separate parallel lines. They are distinct parallel lines. Distinct means different, and shown. So this is the method 2 to perform the second task, assuming that task 1 has been done. I hope this is not too small for you to see. Okay, so I think that's it for this question. Okay, so hopefully everyone can still digest this question so far. And we have been spending quite a long time on this. Right, so basically there are two tasks to do, and to show that there are distinct parallel lines. First is of course to show that the directions are parallel. And so you show that one direction vector is a scalar multiple of the other. Then you conclude that there are two possibilities. The lines are either distinct parallel lines or coincident lines. And then you need to perform the second task where you want to rule out the possibility of them being coincident. There are two methods to perform the second task. Method 1 is to construct a vector directed from a point on L1 to a point on L2. And notice that this vector is not parallel to the two lines. So we name the point as A1 and A2 respectively. Then we construct the vector A1, A2. Then notice that the vector A1, A2 is not a scalar multiple of either of the direction vectors of L1 or L2. And then we say that the vector A1, A2 is not parallel to the two lines. And therefore, they must be distinct parallel lines. Okay. Okay, next is method 2 to perform the second task. Here under method 2, we are trying to show that one point doesn't lie on the other line. The point on L1 doesn't lie on line L2. So this is just the same procedure as what we did on page 6. At page 6 earlier, in example 3, we learned how to check whether a point lies on a line or not. So method 2 will be a procedure which is the same as example 3. Where we just sub the point into the line that we want to check, and then solve for mu 3 times, and check whether the value of mu that you get is consistent or not. Okay, so if you can show that A1 doesn't lie on L2, that means the two lines must be separate parallel lines. Okay. Since they are not coincident, they must be separate parallel lines. Okay, so done. Okay. For information in the past year, I think I've never seen before questions that they ask you to show that two parallel lines are distinct. This is actually pretty challenging. Right, so based on my impression, I think I've never seen before. Okay, so what's more common in the exam is check whether two lines intersect or not. Example 12 is much more common in the past year paper. Uh, how many marks would it be? Like if you're asking about questions like example 11, actually not many marks will be given. My working is long here because I'm showing you two methods for task 2. In the exam, of course, you will choose either method 1 or method 2 only. So if you look at task 1 and task 2 up until the end of method 1, it's actually not very long. I believe only maybe 3 or 4 marks for this question. It's actually not very long. Yeah. And not much things are being done here actually in terms of computation. It's only either 3 or 4 marks. Okay. Yeah, so what's more common in the exam will be something like example 12. Um, checking whether two lines intersect, this is very popular. And also to show that two lines are skew, that is also very popular. Okay. Okay. So they ask you to check whether these two lines intersect or not. Okay, we are now doing example 12. Okay. Check whether the two lines intersect or not. You should recall the procedure that we learned on page 14. First step, equate the equation of the two lines. Second step, pick two equations to solve for lambda and mu. Third step, use the third equation for checking. Fourth step, conclude. Okay. So this is a 4-step procedure. Okay. So first step. Okay, now we want to check whether the two lines intersect or not. Okay. First step, equate the equations of L1 and L2. Just combine the two brackets together, you have 1, 2, 0 plus 1 lambda minus 1 lambda minus 1 lambda is equals to minus 217 minus 3 mu plus 1 mu plus 5 mu. Then you form three equations. Okay. For such kind of question, when there are three equations, it's important to label your equation with numbers. Label your equation as 1, 2, 3, so that later people will know which two equations you pick. When there are so many linear equations involved, if you don't label properly, it's hard for the examiner to know which two equations that you pick. So make sure that your working is reader friendly. Call this equation 1, later only I call them equation 1, 2, and 3. I usually do one more step first before I name the equations. Okay. But you can actually name these equations as 1, 2, 3 at this stage. There's nothing wrong to do this. Usually I will prefer to move the constant terms all to one side. I will prefer to move the constant terms to one side to make the equation simpler first, to make my solving later easier. This is just something that I prefer to do, not a must. Okay. So I will usually move the constant terms to one side first. So this is lambda equals to minus 3 mu. Let's call this equation 1 then. This is minus lambda equals to minus 1 plus mu. Call this equation 2. And This one is already in a nice form, so let's call it equation 3. No. Okay, so that's the first step. Form 3 equations by equating the equations of L1 and L2. Next, solving equations, pick 2 equations to solve, and I strongly suggest you to mention the phrase solving 1 and 2 if you are picking 1 and 2 to solve. You can of course pick 1 and 3 or 2 and 3. Once you pick a pair, you stay loyal to the pair that you pick, which means in the process of solving for lambda and mu, don't touch the equation that you didn't pick. I repeat, don't touch the third equation. Once you touch the third equation, everything, whatever that you get at the end, it will be regarded as wrong because it's a wrong procedure already. Okay. Now I pick equation 1 and 2 to solve. Okay. So focusing on the equations 1 and 2, you can solve those two linear equations by substitution or elimination, whichever you prefer. I choose 1 plus 2 and find that to be easy. I get 0 on the left. This will be negative 4 minus 2 mu, which means 2 mu is minus 4, which means mu is minus 2. And then sub mu equals minus 2 into equation 1 or 2. Don't ever touch equation 3. I repeat, don't ever touch equation 3. Okay, warning, don't touch equation 3. Okay, I sub it into equation 1. I have lambda equals to minus 3 times minus 2. Then lambda would be 3. So at this part here, don't ever touch equation 3. Equation 3 is reserved for checking. Then next step, to this sentence that I underlined in purple, I also strongly suggest you to write down so that you yourself know what you are doing. Check whether mu equals to minus 2 and lambda equals to 3. Satisfy equation 3. Okay. So you would write left hand side of equation 3 is minus lambda. You can actually sub the value of lambda straight away. I just choose to do it a bit slower. I just copy minus lambda first and only I write minus 3. It's actually okay to jump. And then you write right hand side of 3. Seven plus 5 mu, which is 7 plus 5 by minus 2. That gives you also minus 3. And they are the same. Right? So you say, since left hand side of 3 is equal to the right hand side of 3, mu equals to minus 2 and lambda equals to 3, satisfy equation 3. And therefore, the system of equation one, two, and 3 It has a unique solution for lambda and mu. Okay. This sentence in yellow color, what I mean by a system of equation, it means the equation 1, 2, and 3 solved together as three simultaneous equations. Okay. So that's the meaning of system of equation. System of equation means the three equations solve as three simultaneous equations. Okay. Then, what I mean by unique solution means there is one specific value, one specific pair of values, mu and lambda, that satisfies all three equations. Unique means one and only one. And so mu equals to minus 2 and lambda equal to 3 is the only pair. It's the only pair of mu and lambda that satisfy all three equations. Okay, so since there is only one pair of mu and lambda that satisfy all three equations, that means that the two lines intersect at one point. Right, then at the end we can conclude, therefore, L1 and L2 intersect. Okay, so here's the final conclusion. Whether this checking procedure check whether two lines intersect or not, when you do the homework question later in this chapter, you are going to apply this procedure many times. It's very popular in the exam. So it's always a four-step procedure, right? So the first step, equate the two equations. Second step, pick two equations, solve for lambda and mu. Third step, use the value of lambda and mu, sub into the third equation, check whether left is equals to right. Okay. Then after you check, write the conclusion. Write the conclusion. Right, so this will be, these are all the conclusion part. These are all the conclusion. Okay. Now, this question is not done yet because there is a last requirement which says if they intersect, if the two lines intersect, find the intersection point. Okay. So here they indeed intersect, so we have to perform the last task. Okay. So find the coordinates of the intersection point. But to find the intersection point is the easiest thing to do after you show that they intersect. Yeah, because you know that uh, lambda equals to 3 and mu equals to minus 2. And these are the only pair of solution that satisfy the three equations 1, 2, and 3. This is the only pair of solution that satisfy all three equations. So to get the intersection point is easy. You just need to use either lambda equals to 3 or mu equals to minus 2, either one of these two. Just sub it into equation of L1 or L2, whichever you prefer. You don't have to do both. Because if you sub lambda equal to 3 into the equation of L1, you will get an answer, and that answer will be the same if you sub mu equals to minus 2 into the equation of L2. So you just need to pick either one to use. You don't have to use both, because both will lead you to the same answer. Okay. So they didn't name the point of intersection, so I call it I. Let I be the point of intersection. Then OI will be equals to, here I'm using the equation of L1, 1, 2, 0. Lambda is 3, so I just type in 3. 1 minus 1 minus 1. That will be equals to 4 minus 1 minus 3. They ask for coordinates, so therefore the coordinates of the point of intersection in coordinate form, 4 minus 1 minus 3. Okay, done. So here I'm actually using used equation of L1 and also sub lambda equal to 3. Okay. You can also use equation of L2, and in that case you would sub mu equals to minus 2. It will lead you to the same answer. You can try. And you just pick either one of the two lines to use when finding the intersection point. And you don't have to do both. Okay, now we move to example 13. Okay, you have vector equations of the two lines L1, L2 given this way. The two lines intersect at a point. And now you are told that the two lines intersect. You are told that the two lines intersect. This means later when you form equations 1, 2, and 3, equations 1, 2, and 3, they will have a unique solution for lambda and mu. Because you know that the lines intersect. If the lines intersect, the three equations that you form later, they will definitely have a unique solution. And that allows us to solve for alpha. Okay. Now, first of all, let's rearrange the given information into a more familiar form. L1 is R equals to 9 alpha 4 plus lambda minus 8 minus 3, 5. Here they didn't write it. Okay, actually they give us lambda mu in R, yeah. But I think I told you before, sometimes the exam question, they may omit mentioning lambda in R. Yeah, so even if they don't mention this, it's understood that lambda is a parameter that takes all real values. Okay. L2 minus 16 minus 3, 10 plus mu times 1 minus 4, 9 mu in R. Okay. Now we will equate the two equations first. We'll equate the two equations to form three linear equations in terms of lambda and mu. Equate the equations of L1 and L2. 9 alpha 4 minus 8 lambda minus 3 lambda plus 5 lambda. Okay, then you can get three equations. So again, I choose to move all the constant terms to one side first to make the equation less messy before I start to solve. Uh, Minus 25 plus mu, call this equation 1. Now, since we know that the lines intersect, since the lines L1 and L2 in the system of equation 1, 2, and 3, it must have a unique solution for lambda and mu. Now we'll pick two of the three equations to solve for that specific value of lambda and mu, and we know that whatever value of lambda and mu we get later, it must satisfy the third equation. So the problematic alpha here is at equation 2, so we better avoid equation 2. We pick equation 1 and 3 to solve first. Okay, so we say solving 1 and 3. Here I choose to use elimination method. No, I mean substitution method. From equation 1, I have mu equals to 25 minus 8 lambda. Into equation 3. And sub lambda equals to 3 into the equation mu equals 25 minus 8 lambda. Okay, so you have mu equals 25 minus 8 times 3, mu equals 1. Okay. Now we know that this lambda and mu that we get, it must satisfy the equation that we didn't use just now. Right? Lambda equals to 3 and mu equals to 1. It must satisfy equation 2. Okay. So let's sub into equation 2. That's minus 3 lambda equals to minus 3 minus alpha minus 4 times mu. This is minus 7 minus alpha, and you get alpha equals 2. And that's the final answer. Okay. Well, the time is now 10:44. We have about 15 minutes left, but I think we have covered quite a lot today. Uh, so I think I will not proceed with example 14 today. Um, right. Before I end today's lesson, let's recap what we have covered so far uh, in the recent few pages. Example 14 on the next page. Uh, you can attempt it on your own first. For to show that L1 and L2 are askew, there are two things to show. First is to show that the lines are not parallel. Second is to show that they don't intersect. Right, so you can attempt this on your own first. I will show you the answers uh, during our next lesson on Tuesday, for example 14. Okay. For shortest distance, I think you also know the idea already. You find the foot of a perpendicular first. Okay. Then, right, so let's have a recap before we end the lesson today. Okay. Okay, so at the beginning of this chapter, for 3D lines, we first will introduce the vector equation of a line. Okay. Okay, so a vector equation, to write down the vector equation, you always need a fixed point on the line and also a direction parallel to the line. Then you can always write R is equals to the vector OA plus lambda times B, where lambda takes all real values. Okay. Then next, we learn the interaction between point and line. Okay. Given an external point P, okay, the very popular thing to find is the foot of perpendicular, which I call it F. Let's just suppose that L here is R equals A plus lambda B. Okay. So the procedure for finding foot of perpendicular, first step is always to note that F lies on L. F lies on L, then you can write OF is equal to A plus lambda B. So you will get something in terms of lambda. Next, form the vector PF. PF will be OF minus OP. After some computation, you also get something in terms of lambda. Next, make use of the fact that your PF and B are perpendicular. So you can take PF dot B equal to 0. Okay, then solve for lambda. Then finally, whatever lambda that you get, let's say you get lambda equals to a question mark, then you will sub lambda equal to question mark back into the expression for OF. Okay, then that gives you the position vector of F and hence the coordinates of F. Okay, so this is a 4-step procedure. Okay. This is the first step, second step, third step, fourth step. Okay, a 4-step procedure to solve for foot of perpendicular. Okay. Then once you get foot of perpendicular, there are two other things that you can find. Okay. Once you get F, you can always find the distance PF. Okay. Yeah, I'm basically just repeating things that we have covered before. Yeah, so yeah, you don't really need to jot this down if you can already remember the procedure. Yeah, but anyway, thank you for helping the screenshot. Okay. Okay, so after you have the foot of perpendicular F, um, right, you can find the distance PF, and this will be, of course, the length of vector PF, right, and this is also the shortest distance from P to line L. Okay. That means if question asks for shortest distance from point to line, you will first need to find the foot of perpendicular F first. And then the same 4 steps will be applied again. Okay. Then there's also a third thing. when you have the point F already found, you can also reflect the point P in the line L, making use of midpoint. Then you can get P prime. F will be the midpoint of P prime. Okay. And so these are the three things that you need to know about point and line. Foot of perpendicular, shortest distance, and reflection of a point in the line. Okay. Then we also learn about line and line, interaction between two lines. So first thing is about intersecting lines. Okay. Where you have to know how to check whether two lines intersect or not. This is again a four-step procedure. First step, equate the two lines. Equate L1, L2. Then form three equations. Second step, pick two equations to solve for lambda and mu. And warning, in this step, do not touch the third equation. Do not touch the third equation that you didn't choose. Okay. Because the third equation is reserved for checking. And then step 3, check whether lambda equals to something, mu equals to something that you got just now. Satisfy equation 3. I mean the third equation. Depending on which is the third equation that you didn't use just now. Right? Okay, then step 4, conclude. Okay. Right, so this is also a four-step procedure to check whether two lines intersect or not. Okay. Okay. Then we also learn about parallel lines. Okay, so if direction vectors are parallel, you can have B1 this way, B2 the other way. If B1 is parallel to B2, then there are two possibilities. They can be distinct parallel lines or coincident lines. And if you want to rule out the possibility of them being coincident, example 11, we have learned how to do that. There are two methods. First method is to construct a vector directed from A1 to A2, then show that A1, A2 is not parallel to B1 or B2. Second method is to show that A1 does not lie on L2. Okay. So depending on your preference, you can either use method 1 or method 2 to perform the second task. Okay. Then, and lastly, for skew lines, there are two conditions to show. Skew lines require two conditions. To show that two lines are skew, you need two conditions. First condition is that the lines are not parallel. L1, L2 not parallel. The second thing to show is that L1, L2 don't intersect. Okay, so to show this one, to show L1, L2 don't intersect, you have to go back to the four-step procedure. You have to go back to the four-step procedure over here. You have to go back to these four steps to show that the two lines do not intersect. Right, so to show that two lines are skewed, the working can be quite long. And most of the time, it's either 4 or 5 marks allocated for such kind of question. Okay. Right, I think this is a summary. This wraps up what we have covered so far in this chapter. And also don't forget the length of projection. Although it's not so frequently used in chapter 9b, it will be used quite frequently in FP1 vectors. Right, the length of projection And make sure you don't forget that because we'll use it in FP1 vectors quite frequently. Right. That's all for today. We'll continue with example 14 on Tuesday. I'll see you again on Tuesday. Right. Yeah, thank you everyone. You may leave the video meeting.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Have a nice day.